In this lecture, we look at the physics behind the inductor behavior. In particular, why does an inductor behaves the way it does? So the relationship between the voltage and the current across an inductor is given by this equation where V is equal to L into di by dt. So as far as the circuit behavior of the inductor is concerned, this equation is all there is to know, and it can be used to solve the circuit behavior. But to have an intuitive understanding and a physical understanding of why the inductor behaves is something that is good to have. So in that respect, we first need to have a brief understanding of electromagnetic force. So just like a gravitational force, electromagnetic force is also a fundamental force, one of the basic forces in nature that we are always subjected to. So there are two types of electromagnetic forces. One is related to the electric field and the other is called the magnetic field. The electric field is caused by static charges, and magnetic field is caused by charges which are moving. So now we come back to the behavior of an inductor. So let us say that if we take a loop and form in a shape like this and push a current I0 through this loop. So from electromagnetics, what this tells is that a moving charge like this also produces a magnetic field, and the direction of this magnetic field, for example in this case, is through the loop coming from the pitch towards the viewer. So it's coming outside the I have tried to show like this here. It's coming out of the page. So that's the direction of the magnetic field. So basically, in short, there's a loop is there in which a current goes in this direction, and it creates a magnetic field. So now the electromagnetic forces are governed by what is called Maxwell's laws, and a simplified Maxwell's law in terms of can be phrased as below. So when there is a change in the electric field, it produces magnetic field, and this is often denoted by a quantity called by a notation B. And when there is a change in the magnetic field, it produces electric field, and this in a way is responsible for the inductive behavior, this second relationship. So what happens is that in a loop like this, when there is a static current I0 flowing through this, it produces a magnetic field in the direction coming outside the paper. Now if we try to change the current flowing through this loop, that will try to change the magnetic field. So for example, if you want to try to increase this current from I0 to I0 plus delta I0, it will try to increase the magnetic field from B to B plus delta B. So think of it in terms of qualitative, that increase of current increases the magnetic field. Now the Maxwell's equations tells us that if the magnetic field changes, it produces an electric field which tries to oppose the change of this magnetic field. In other words, the increase of the current increases the magnetic field. The magnetic field tries to produce an electric field, or in other words, uh, a, an opposing force in this loop to oppose the change that was trying to increase the magnetic field. So the net result is that this electric field induces an EMF or a voltage drop, voltage in this loop, for example, like this, which opposes the flow of the current, increase of the current. And the magnitude of this induced voltage in the loop is proportional to how fast this current is trying to increase, and also to the and that proportionality is called the inductance L. And similarly, if we try to, for example, reduce if we try to reduce the current, this I naught, in that case the magnetic field will try to reduce. The reduction in the magnetic field will induce a voltage in this loop, which will try to restore the magnetic field back to its original value. So basically nature does not like the change that is happening, and it induces conditions to restore to its original state. And to do that, it will induce a voltage in this polarity, which will try to increase the current again back to its original value. So in a sense, and the magnitude of this voltage will again be proportional to the rate of change of the current and the inductance value. So in a essence, what the inductive behavior is trying to do is it's trying to oppose the change in the current.